Hello, today we're going to talk about how to solve optimization problems that are written in continuous time. What we're going to look at is often referred to as optimal control theory because we're going to think of controlling how a continuous function changes over time. We'll be controlling its derivative or some function of its derivative. The way we're going to do it is going to look at some very beautiful mathematics, I think, that turns out to give us some very powerful implications for what necessary conditions the optimum must satisfy in this context. And we'll do it because later on this is going to be opening a door to techniques that we can use to think about growth models in continuous time, as well as many other kinds of problems. Let's take a look. So what we're going to do today is to try and approach continuous time maximization problems. And the problems that we're going to look at will have the following form. At each point in time, there will be a function that provides some kind of benefit, maybe a utility function, for example, or profit function, f. Now that function is going to depend on several things. One, it will depend on a variable we're going to call the state variable, and that is going to be x. However, as mentioned, this is an environment where there is time, and so x is going to depend on time. For example, it could be physical capital or human capital. Second, it's going to also depend on the derivative of the state variable with respect to time. And third, it may depend on time itself. So this is the instantaneous return, profit, utility that our agents earn, and they are going to maximize this by controlling this state variable over some time interval. In principle, that time interval could go from, let's say, 0 to some finite date t. But what we're going to do, because this is going to be relevant to many economic problems, is say that this is infinity. And where relevant, we'll discuss how having finite horizons might change anything. So this is the problem that we're going to deal with. Now, one thing that's going to be analogous to the problems that we used earlier in discrete time is that there is going to be one constraint here, which is that the initial value of our state variable is given. So you don't have control over that. Again, here we refer to x as the state variable. An approach to dealing with this kind of problem is referred to as optimal control. And the way optimal control approaches this kind of problem is by introducing a new variable, u, little u, and we're going to set that equal to x prime. Then we can rewrite this problem in the following way. We can replace the x prime there with u and add the new constraint, which is just that u equals x prime. Finally, we can generalize this by saying that what if rather than u being equal to x prime, u is equal to some function that depends on all of these arguments: x itself, the value of u itself, and time. Now it should be clear that this fits under this umbrella, because of course if I take f and plug in g here, it should be clear that this is equal to some other function f that ultimately depends only on these arguments. So in any case, many economic problems are going to take this form. Once more, it should be clear that that maps directly into this form, and so we don't need to worry about it. This one, on the other hand, actually looks more general, so let's go with that. So, how are we going to solve this? The answer is that we're going to solve this in 3 steps. The first step is to make an observation. The observation is as follows. For any state variable x, control variable u, and any continuously differentiable function lambda, the following must be true. Take this, which is the function that we want to maximize. That must be equal to the following expression: f itself, the integral over f itself, plus lambda times g minus lambda times x prime. The reason this has to be true is because this minus this equals 0 by definition. Now let's rewrite this by separating out the last term from the others. So I take this out of the integral, and of course, for this to be correct, I have to integrate it too. So far, so good. Now let's integrate the last term by parts. Not between 0 and infinity, but between 0 and some number t. So let's take this term, but we're integrating up to big T. Of course, if we had a finite horizon, then this would be sufficient. We have an infinite horizon, so we have to do a little extra work. We integrate this by parts. What we're going to get is that this is equal to lambda times the integral of x prime, which of course is x, evaluated at the limits of integration 0 in big T, plus, normally it would be a minus, but there's a minus sign in front of everything, the integral of lambda prime and the integral of x prime, which is x. Now let's take the limits as t goes to infinity. Again, this step is not necessary if we have finite bounds. And what are we going to get? This just goes to infinity. This, of course, can be written out. This is just that evaluated at 0 minus this evaluated at t. This doesn't depend on t. So here we have the limit as t goes to infinity of this, and then this just goes to infinity. Great. So if we put this and this together, what we end up with is that f is equal to this expression and plus this expression. We can put this on a separate line so that it's not too wide. Easier to see. Great. The next thing we're going to do is optimization. We're going to propose an optimal path for x. So let x star be an optimal path for x, and let u star be the corresponding control variable. Consider once more some arbitrary differentiable, continuously differentiable function h, along with some real number a. What we're going to do is to use h, which is arbitrary, and a, which is also arbitrary, to try and construct alternatives to x star and u star. So consider an alternative control variable u star plus a times h. Of course, if a is 0, then we have u star itself. If a is small, then whatever h is, we're still not far away from u star, and so we're going to call u star plus ah a variation on u star. Let y of t and a equal the path of the state variable induced by our variation. Again, if a equals 0, then yta equals x star. If a is very small, it shouldn't be far off. Next, define the value of our objective function as a function of a. And let's call it j of a. And that's going to equal this, except that where we see x, we need to insert ya, and where we see u, we need to replace our variation. Ensure that we're inserting time as our arguments. Now we can rewrite this using some arbitrary continuously differentiable lambda. How so? Well, here is our definition for j. We can rewrite it as here. So how would we do that? Well, this first part we already have. This is the part that we're missing. So first of all, let's add some parentheses. What we need to do is, again, wherever we see x, we write y, and where we see u, we write our variation. In addition, we need these terms. This stays the same. Again, remember, where we see x, we need to write y. Now, why didn't I change this for y? We could do that for consistency. However, remember, one of the conditions of this optimization problem is that x0 is given. So no matter what is the value of a, no matter our variation, this number is not going to change. Finally, we have to write y there. Very good. Next, recall that x star and u star maximize the objective function. So that means that since u star maximizes our objective function, it must be that j prime evaluated at 0 is 0, since everything here is differentiable. So now let's figure out what j prime is and set it to 0. Okay, what do we do here? Well, a shows up both in the first argument of this and in the second argument. So when we differentiate this by a, maybe we want to use some compact notation to try and avoid this being too complicated. So the first derivative of f is, or rather, the derivative of f with respect to its first argument is f of x, because the first argument is the state variable. And that we have to multiply by the derivative of this with respect to a. Let's call that y sub a. Then again, we have to differentiate f with respect to its second argument, because a is there. Let's call that f sub u. And then what's the derivative of this with respect to a? It's h. Just write h. So I'm suppressing the argument t here. Next, we have to differentiate this term with respect to a. And once more, it shows up both in the first argument and the second argument. So we're going to get lambda times g sub x times y sub a plus lambda t times the derivative of g with respect to the second argument, g sub u, times the derivative of that with respect to a, which is just h. So we're done there. This is a constant. It doesn't depend on a, so its derivative with respect to a is, that's right, 0. The derivative of this with respect to a is just y sub a and the derivative of this with respect to a is just also y sub a. Now let's collect some terms To make this a little more organized, we can put this back inside the integral. And first collect all the terms that have a YA in front of them. So here this has a YA, Y sub A that is. And now we can factor out Y sub A. Next, we can group the terms that have H. That's, of course, these two terms. Factor out the H. And there we are. So far, so good. Next, we are going to make an intelligent choice of lambda. Now, so far, lambda has just been continuously differentiable, but that means that it should hold for any particular lambda that we would like to explore. So we're going to choose one that's going to give us further insights. Define lambda so that it satisfies the following. First, lambda prime is going to equal minus f sub x minus lambda g of x. This is just a simple differential equation with a simple solution since it's linear. And it satisfies the limit as t goes to infinity of lambda t equals 0, where the derivatives are evaluated at x star and u star. Now we plug this into the expression for j prime at 0. Here is that expression. Plug in our lambda. So lambda prime equals this. And what happens? All of this becomes 0 with that particular choice of lambda. What else happens? The limit of this is 0, and so this term disappears as well. We're left with a much simpler expression. And finally, we set this equal to 0. We have the following condition when a equals 0. Next, just as we were able to make an intelligent choice for lambda, let's make an intelligent choice of h. And in particular, suppose that h of t equals f sub u plus lambda g sub u, all evaluated at x star and u star. Then this condition becomes, well, notice that this is the same as what's in here. So what we end up with is just that squared. That has to be true for this particular choice of h. Now notice that the only way this can be true because the slightest deviation of this from 0 will be squared and will thus result in a positive value here. So the only way this can be true is if this that is inside is equal to 0 for all t. Now that is a pretty powerful condition that we have shown. So we have shown that for optimal x star and u star, there exists a function lambda such that together these three functions satisfy the following conditions. First condition is what we're going to call the state equation. That is just the equation that x prime equals g of x u t. With, of course, x0, with, of course, x0 given. Second condition is referred to as the co-state equation, or sometimes the multiplier equation. And that's this, the definition of lambda, our intelligent choice. Third is the optimality condition, or optimality equation, which is this. Pretty powerful stuff. These are all necessary conditions for an optimum in this environment. And all of them are pretty straightforward to compute in the case of any particular application. We'll look at some examples together later on. Now, this may remind you somewhat of Lagrangian or Kuhn-Tucker conditions. There is some multiplier-like function, lambda, that really helps us get a handle on how to solve any optimization problem in the relevant context. In those cases, there is the Lagrangian function that you set up as a way of trying to remember how to regenerate all the necessary conditions for finding your optimum. So in this context, we also have a mnemonic device to recover these conditions, sort of like the Lagrangian, and it's called the Hamiltonian. Hamiltonian is defined as follows. Let's call it h of x, u, and t. And it is the objective function, f x, u, t, or rather the instantaneous, the integrand in our objective function, plus lambda g. And the solution to our maximization problem necessarily satisfies these conditions. First, we need the derivative of the Hamiltonian with respect to the control variable to equal 0. That's intuitive. Next, we need the derivative of the Hamiltonian with respect to the state variable to equal minus lambda prime. And third, we need the derivative of the Hamiltonian with respect to lambda to equal x prime. Now, how do these conditions help us? Well, let's take them one by one. First, let's look at this condition. If we put the Hamiltonian in here, set that equal to 0, if we're going to differentiate f with respect to u, we get the derivative of f with respect to its second argument. The same is true of g. We differentiate this with respect to u, we get the derivative of g with respect to its second argument. And what have we done here? We have recovered the optimality condition. Is the optimality condition. Next, let's take this second condition. Let's insert the Hamiltonian. The derivative of f with respect to x is just its derivative with respect to the first argument. And again, the same is true of g. So what do we have here? We have recovered the costate equation. And last, let's take this condition, replace here the Hamiltonian with the expression for the Hamiltonian. This is easy to derive with respect to lambda. The derivative of f with respect to lambda is 0. And the derivative of this expression with respect to lambda is just g. And we have recovered the state equation. So in this way, you can use the Hamiltonian, remember this, and you can get all the necessary conditions you need for an optimum. One thing that you should not forget is that we also need one more equation here, which was the condition for what happens at the end of time. Lambda must converge to 0 over time. If we were in a context with a finite horizon, then the analogous condition would simply be for this to hold. And that's it. We now have necessary conditions for solving continuous time optimization problems. So far we've been talking about necessary conditions for an optimum, and you might wonder whether there are contexts where these conditions might also be sufficient for an optimum. Well, it turns out that there is one very intuitive condition under which all of these conditions turn out to be sufficient as well as necessary, and that is if it turns out that the Hamiltonian is concave when evaluated at the optimum that you are proposing. In other words, what you need to find is whether the second derivative of the Hamiltonian with respect to the control is negative. And if so, then we're in business.